Hello everyone, welcome back. In this presentation, we are going to focus on the relational algebra, the set intersection operation. We have already seen about all the 6 fundamental relational algebra operations in the previous lectures: the select operation, the project, union, set difference, Cartesian product, and the rename operations. Now we are going to turn our attention towards knowing the additional operations. I mean the additional relational algebra operations. What are the operations that we are going to see in the coming lectures? The set intersection operation, the assignment operation, the natural join, then division operation, and then the outer join. In outer join, we are going to focus on the left outer join, the right outer join, and the full outer join operation. And in this presentation, we are going to focus on the first additional operation, the set intersection operation. Let's see the basics of the set intersection operation now. We know basically any relation is a set, and that is why it is named as relational algebra, because it has a close correspondence with the mathematical concept, the set theory. So when we say that any relation is a set, then obviously all the properties that are applicable for the set, that is also applicable for relations. And obviously in set theory, we have the set intersection operation. Likewise, this set intersection is applicable in relational algebra also. And that's why the second point says, this set intersection is similar to the same intersection operation in set theory. And what type of operator is this? Whether it is a unary operator or a binary operator. Set intersection is going to combine the output of two different sets or two different relations. Then obviously it is a binary operator, which takes two operands as input and produces one output. Here the operands are two different relations. And what's the basics of this set intersection operation? Actually, this set intersection is a set of all objects that are a member of both A and B. Say if we have two relations A and B, then the output of the set intersection operation is A intersection B, which contains the members that are belonging to both the set or both the relations A and B. Anyway, when we see an example, then it will be easy for you to understand. And this set intersection is denoted by the inverted U, which is this symbol. Let's see the syntax with an example now. So here what we are doing is, we are taking relation 1 as one of the operands, and we are projecting a column or a set of columns here. So what we are doing here is, we are simply projecting a column from relation 1. And similarly, we are projecting another column or another set of columns from relation 2, and we will be having a temporary relation here. Here also we will be having a temporary relation. And what we are doing? We are doing the set intersection operation between these two temporary relations. Now you may be asking me a question. Why don't we directly use relation 1 set intersection relation 2? This is possible only if the two conditions are met. We have already seen about those two conditions in the previous lectures when we have dealt about the union and the set difference operation. What are they? They are, first, relation 1 and relation 2 must be of same arity. It means whatever the number of columns in relation 1 we have, the same number of columns we need to have in relation 2. At the same time, the domain of the ith attribute of relation 1 is same as that of the ith attribute of relation 2. So if these two conditions are met, then we can directly apply set intersection. But there are situations where we need to retrieve certain information and then perform set intersection. So here what we have done, we have simply projected a column or a group of columns from relation 1, set intersection, again projection of column or a set of columns from relation 2. Then we can easily perform set intersection. I hope the theoretical basics are clear to you now. Let's see the basic working of the set intersection operation. Then we will proceed with the example. To understand things, I am bringing in the first set or the first relation R, which contains alphabets A, B, C, D, E and F. So this is input number 1. And let's take another input, which is S, where it contains some group of characters A, B, $, E, F, 1 and hash symbol. Now we have two inputs, R and S. If we want to perform R intersection S, then the condition should be, the arity should be same on both the relations. Here R, the relation R, which is containing only one column. Similarly, S is also containing one column. And coming to second condition, the domain of this column is same as that of the domain of this column. Hence, we can apply the set difference operation where we are going to perform R intersection S. And here is the output of R intersection S. How did we get this output? What is R intersection S? It is the set of all objects or elements that are the member of R as well as S. The elements in the output will be belonging to both R and S. When we take R as an example, we have A here, we also have A here, and hence A is there in the output. Coming to the next value B is here in R as well as in S. So B will also be there in R intersection S output. And coming to C is there in R but not in S. So C will not be there in the output. And that's why we are not able to see the element C in the output. And coming to the element D is there in R but not in S. And that's why we are not able to see D in the output. Coming to E and F, both E and F are there in R as well as S. And hence we can see E and F are there in the output. So what do we understand from this is R intersection S is a set of all objects that are the members of both A and B. In this case, the output R intersection S will contain the set of all elements that are the member of both R and S. With this basic understanding, let's move on to example number 1. Here is the example. We are required to find the names of all customers who have deposited money and also availed loan. I request you to pause this video for a while and think what is expected in this question. I hope you are done. So what we are required to find is, we are required to find the names of all customers associated with the bank. These customers should have deposited the money as well as they should have availed loan. So what do we understand from here is, we have two relations. One is the depositor relation, another one is the loan related borrower relation. And we are required to take the output of all customer names who has deposited money in the bank as well as he or she should have availed the loan. So what we can do, can we directly perform depositor intersection borrower? No, because the depositor relation may have the number of attributes which may not exactly matching with the other relation, which is the borrower relation. So we cannot directly do depositor intersection borrower. But what we are required to do is, we are required to list the names of all customers from the depositor account or from the depositor relation, and then intersection list all the names of the customers from the borrower relation. So the solution for this question is, we are just projecting only customer name from which relation? The depositor relation. So here we will be getting a temporary relation which contains only one column, which is customer name. So all the customer names from the depositor relation will be listed here. So all the customers who have deposited money in the bank will be listed here. And coming to this side, we will be getting the list of all customers who have availed the loan. So here we will be getting all the customer names who have availed the loan. But what we are asked to find? We are asked to find the names of all customers who have deposited the money as well as availed the loan. And that's why we are using intersection here. So let's see an example. Let's take the depositor relation which contains two columns, the customer name and account number. Tom with the account number A101, Amy with A502, Rose with A304 as the account number, and John with A689 as the account number. So this depositor relation contains 4 tuples. And coming to the other relation, which is the borrower relation, this borrower relation also contains 4 tuples, but it need not be the case that the number of tuples should match on both the relations, but the condition is the number of columns on both the relations should match. In this case, even if there are differences in the number of columns in both depositor and borrower relation, this will still work because we are projecting only customer name here and customer name here. So the output contains only one column here, and this output also contains one column. We are doing intersection between a relation with one column with another relation with one column. And in borrower relation, we have John, Smith, Rose and Jack with corresponding loan numbers. And what will be the output of this relational algebra expression? For simplicity, I am giving a temporary name for this output as R. And again, this side I am giving the name S for simplicity. So R will contain only one column, which is customer name. And S will also contain only one column, which is also customer name. Now we are going to perform R intersection S, which is customer names from both the relations. If you see here, this output will contain a relation with one attribute, and this output will also contain one relation with one output, and we are performing set intersection. Since the number of attributes are same on both the operands, it can be performed at the same time. This is also customer name and this is also customer name, and we can confirm that condition number 2 is also getting satisfied because both the attributes are belonging to the same domain. So we got R intersection S with the output Rose and John. Why Rose and John and why not others? Because Rose has deposited the money in the bank, as well as Rose has availed loan from the bank. Coming to John, John is a depositor as well as a loan borrower. And that's why we can see Rose and John are there in the output. Why not Tom and Amy? Because Tom and Amy are merely depositors but not borrowers. And what about Smith and Jack? Smith and Jack are just borrowers, not depositors. So set intersection can also be inevitable in certain situations. I hope this example is clear for you. Now let's proceed with the example that we have been dealing in the previous presentations, the formal example which deals with the university database. What about the database schema? It has multiple relations: the instructor relation, the course relation, the department relation, the section relation, the teachers relation, student relation, advisor relation, takes relation, classroom relation, and the time slot relation. Now let's focus on the formal example. In example number 2, we are going to find the set of all courses taught in fall 2009 semester and the spring 2010 semester. I request you to pause this video for a while and think about the answer for this question. I hope you are done. So this is a pretty straightforward question because we have already seen similar kind of examples in the union and the set difference operations. So the solution for this question is going to be like this. First, we will list all the set of courses that are taught in fall 2009 semester. So what relation we are going to take? It's the set of all courses taught, not related to instructor. So we are not going to take the teachers relation. Rather, we are going to take the section relation which contains all the courses taught in a particular semester. So the output is, first we will find the set of all courses taught in fall 2009 semester, which is this part. And what output we want here? Only the set of all courses. So what we will do is, from the section relation, we will filter all the tuples which are belonging to the semester fall and the year 2009. And that output will contain all the tuples that are belonging to fall 2009, but it will also contain additional attributes, all the columns. We want only course ID. So here we will apply a project and filter the course ID. Let's see the output now. So first what we are doing is, from the section relation, we are just filtering, we are just selecting all the tuples where the semester is fall and year is 2009. So this output will be giving a relation which contains all the tuples with all the attributes where the semester is fall and year is 2009. I mean, we are dealing this part. And from this output, we are filtering only the course ID. So I am just projecting only course ID here. So this is pertaining to fall 2009 semester. And likewise, we need to retrieve the records pertaining to spring 2010 semester. So what I am gonna do now here is, I'm gonna find out the set of all courses taught in spring 2010 semester. And the query is simple. The same select operation where the semester is spring, because this is spring, and the year is 2010, which is this, from which relation? Section relation. Again, this inner query will give all the tuples which are belonging to spring 2010 from section relation, and we want to project only course ID because our intention is to find all the courses. So here I am giving a project for this inner query by retrieving or by projecting only course ID. Now we have two relations. This is relation 1 and this is relation 2. And what we are required to find? We are required to find the set of all courses taught in fall 2009 semester and spring 2010 semester. It means the course that are handled should be there in both fall 2009 and spring 2010. Say for example, if DBMS is the course, this DBMS course should be offered in both fall 2009 semester and spring 2010 semester. So the output should be appearing in both the relations, and that's why we are performing the set intersection between these two sets or relations. To answer the query, we need the intersection of these two sets or relations. So the output is, I'm just projecting the course ID. So this is the first half, which is this, and this is the second half, which is this, and we are simply performing intersection so that the output will contain the set of all course IDs taught in both fall 2009 semester and spring 2010 semester. I hope this example is clear to you. Before we sign out, we need to understand the important thing about the set intersection. Can we do the set intersection operation without set intersection operation? Confusing? I mean to say, imagine we don't have set intersection operation exclusively. How can we achieve the functionality of the set intersection operation without using this operator, the intersection operator? Is that possible? Yes, it is possible. Let's see that now. We have already seen about the basic concepts of the set intersection. Now this set intersection can be achieved without using the set intersection operator. How? It is R intersection S gives the same output as that of R minus S. We know what is minus, the set difference. First we need to perform R minus S, and then this is the output which is going to be applied on R minus. It means R intersection S is equal to R minus S. Don't worry about this, we shall prove this now. So what we are going to prove now is R intersection S is equal to R minus S. So let's bring in this formula and let's take the first relation R, which is containing the set of alphabets A, B, C, D, E and F. Let's take another set or relation which is S, which is containing set of characters A, B, $E, F, 1 and hash. We have already performed R intersection S in our previous slide, and the output of R intersection S will be the set of elements A, B, E and F, where A, B, E and F are the elements that are there in both R as well as S. Now what we are required to do is R minus S. First we will compute this R minus S. So we are just applying R minus S. What do we mean by R minus S? R minus S will give the output where the output will be the member of R but not S. If you see the elements A, B, E and F, these members are there in R as well as S. R minus S will give the output where they are the member of R but not S, right? C and D are the members of R but not S. Can you see C and D are not there in S? So obviously R minus S will give C and D as the output. So R minus S we have computed. Now we will perform R minus S. It means we are going to perform R minus S. And this output will be giving A, B, E and F because this is C and D. This is A, B, C, D, E and F. Now R minus S means the set of members of R but not R minus S, right? C and D are the members of R minus S. Here also they are the members, but A, B, E and F are the members of R but not R minus S. And that's why in the output we get A, B, E and F. If you compare R intersection S and R minus S, both are same. Why we are dealing this basic operation now? In examinations, they might be expecting us to solve this problem without using set intersection. In that case, we need not truly rely on this operator. Rather, we can directly use R intersection S as R minus S. We have already seen about the various fundamental operations. Why we are calling this as fundamental operation is that even the additional operations can be achieved through these fundamental operations. Before we sign out, let's see the homework question. We have 3 homework questions here. Question number 1. Is the relational algebra operation R union S commutative? Question number 2. Is the relational algebra operation R intersection S commutative? And question number 3. Is the relational algebra operation R minus S commutative? I request you to think about these questions and post your answers in the comment section. Before we sign out, I wanted to give you an insight about what is a commutative property. When we take integers as a set, now in this integer, plus is an operator. To be precise, this is an arithmetic operator which performs addition, where this plus operator, the addition operator, is commutative. If we take any 2 elements, say 5 and 10, 5 plus 10 is equal to 10 plus 5, right? So plus is commutative. Take any integers, 200, 500. 200 plus 500 is equal to 500 plus 200. So the operator plus is commutative. Likewise, think logically and answer this question whether this union, intersection and minus are commutative or not as far as relational algebra is concerned. And that's it guys. I hope you guys enjoyed this presentation and thank you for watching.